This lesson is on implicit differentiation. Let's talk about what that means. First of all, if we talk about an equation being in explicit form, what that means is that an equation can be written in the form of y equals something. So that means y can be isolated. But there are situations where it's difficult, if not impossible, to isolate the y. So an example would be something like this. So in that situation, y is difficult, if not impossible, to isolate. So finding the derivative gets a little bit tricky. It's hard for me to talk and write at the same time. So it's tricky then if we were trying to find dy dx, if we're trying to find the slope, it's difficult to isolate the y and then find the derivative. So we're going to use a method called implicit differentiation because it's in implicit form, meaning y is really difficult to isolate, but we still need to find the derivative so we can determine what is happening with the rate of change, the instantaneous rate of change of this graph. Now, a lot of these graphs are no longer functions because a lot of the x values will have multiple y outputs for the y values, but we can still look at the rate of change even though it's not a function. So let's look at an example. If I said, let me find something that's not going to be too crazy. Let's just do this one. Let's just say I have x times y equals 4. I could easily isolate the y. Absolutely, no doubt about it. But what I want to show you, just for the sake of argument, I want to show you how to find the derivative of this in the form that it's in. So in this implicit form, with y not being isolated. First thing I want you to notice, and we haven't really talked about it, I've just been writing it all along. What we're saying here is we are differentiating with respect to x. In other words, I'm saying, how are these values changing as x is changing versus how is time changing or versus some other variable changing? So I'm saying, as x changes, how is everything else changing? So let's use the product rule on this, and I'm going to use a different color so it stands out a little bit more. I'm going to use the product rule on this because that is x times y. Okay, so to use the product rule, I'm going to find the derivative of x with respect to x. And we all know this, we know it's 1, but I'm going to get more formal because eventually we're going to find derivatives with respect to a variable different than x. So in this case, I'm saying, how is x changing? Because we're finding the derivative of this first term. How is x changing as x is changing? So that's the derivative of x with respect to x times y without changing it, plus x unchanged times the derivative of y. So what we're saying is, how is y changing as x is changing? And then since 4 is constant, the change, no matter which variable we're looking at or which variable we're differentiating with respect to, the derivative of 4 will always be 0. So now let's look at this a little bit more closely. dx over dx, these two values are changing at the same rate. So that's why the derivative of x with respect to x is just 1. In this case, I don't know how y is changing. They could be changing at the same rate, but they're two different variables, so I cannot assume it. So I need to leave that variable as it is. This is just change in y over change in x. I don't know if that equals 1 or some other constant, so I'll leave it as a variable. Okay, our goal is to isolate the dy dx so that we can figure out what the slope of this equation is going to be. So we've got y plus x dy dx equals 0. I'm going to isolate that dy dx, so I'll subtract the y from both sides. And then I'll divide by x. So different than anything else we've been talking about this year, the slope in this case is not only determined by which x value we're on, but it's also determined by which y value we're on. It's really interesting. So let's do another example of a graph that we know what it looks like. Everybody will know, well, I hope you know this one. So let's do another example. I'm going to use red this time. I'm going to give you the instructions this time of find dy dx for this equation. Now I hope you know, and let's give it at a point. Let me think it through for just a moment. No, that one's not very interesting. At 1 comma square root of 8. Okay, I hope you know what this graph looks like. If not, you need to know. This is a circle. The circle has a center at 0 because we're not shifting the x or the y. And the square root of 9 is 3, so I know that the radius of this circle is 3. So let's draw this graph, just a quick sketch. 1, 2, 3. And if I draw my circle, please notability, make it a circle. Not bad, not bad. Close enough. If I knew how to, there we go. Close enough. Ooh, that's not even close, is it? You get the idea. Maybe it'd be better if I just did it by hand. And it just looked a little wobbly. Anyway, so what we're gonna do is find the slope of the line tangent to this graph at the point 1 comma square root of 8. So here's that point 1 comma square root of 8, and I need to find the equation or the slope of the line tangent to that point. In order to do that, we're going to find the derivative. So notice the way I'm writing this out. I want you to write these out the same way. If all of a sudden you just give me the derivative, then you're not expressing your work and not showing your steps that you took to get here. So by writing this out, I'm saying I'm going to find the derivative of this. I'm looking for the derivative with respect to x, so I'm going to make sure that those variables match. Okay, now we have to think about chain rule. Because we have an outer function, I'm going to use a different color for this. We have an outer function on this one and this one. And we have an inner function here, an inner function there. We really have to start thinking about that now because we'll be differentiating with respect to different variables. So we really have to keep thinking about chain rule every single time now that we differentiate. Okay, so for this first one, for x squared, I'm going to find the derivative of the outer, that's 2, out in front, without changing the x, and then subtract 1 from that exponent. So I just found the derivative of the outer function, the squared. Now I need to multiply by the derivative of the inner function. The inner function is x, the derivative is dx over dx. Okay, I'm going to do the same thing for y squared. The outer function is that squared, so I'm going to bring that 2 out in front without changing the inner function, and subtract 1 from the exponent. And then I'm going to multiply by the derivative of the inner function. The derivative of y with respect to x is dy dx. And the derivative of 9 with respect to any variable is 0. So remember, the goal was to find dy dx, so this means we're finding the slope. I know that dx and dx both change at the same rate. That's 1, so this is 2x. And you're probably saying, really, do we have to do that every time? And I'll show you in a minute why that is true. Okay, the goal is to isolate dy dx, so I'm going to subtract 2x from both sides. And I'm going to divide by 2y. And when I divide by 2y, the y's will cancel each other out. So I end up with negative x over y. Now the question said, what is the slope at the point 1 comma square root of 8? So let's find that out. We know the x value in this ordered pair is 1, and we know the y value is the square root of 8. So at the point 1 comma square root of 8, the slope is equal to negative 1 over the square root of 8. That's the slope of this tangent line. It depends not only on what the x value is, but what the y value is as well. Okay, let's do one more of these, but this time we're going to differentiate with respect to, actually I'm going to do two more. Let's do one more with the derivative of with respect to x. So not at a point, we're not going to graph this one. I want you to find dy dx for this graph, 3x squared times y plus y equals 8. I'm going to give you a moment. I actually want you to pause this video and actually pause the video. Go try it. Come back when you're ready. Okay, I hope you actually paused this. We're going to find the derivative of this now. This derivative with respect to x. So I'm going to differentiate this implicit equation because isolating y, you could do it, but we don't need to. I'm going to use the product rule here. I know some of you are thinking, well, why don't I just isolate y? You absolutely can, but what good would that do when we get to something that cannot isolate? So we'll just do it on this one where we can isolate, but we're not going to. So we're going to use the product rule. I'm going to find the derivative of 3x squared. We have an outer function, which is the 2, and the inner function is the x. So I'm going to find the derivative of the outer function. I'm going to multiply the 2 out in front, that's 6, without changing anything on the inner function, and subtract 1 from the exponent. Multiplied by the derivative of the inner function, there we go. So that's the derivative of 3x squared times y without changing it, plus, now the 3x squared I will not change, times the derivative of y, which is dy over dx. So this whole thing was a result of my product rule. Okay, now we're going to move on. We're going to find the derivative of this part. The derivative of y with respect to x is dy over dx. And the derivative of 8 with respect to any variable is still 0. Let's simplify this a little bit to make it look not so gross. So the dx over dx, that's just 1. This becomes 6xy plus 3x squared dy dx plus dy dx. Remember, our goal is to isolate the dy dx. So I'm going to move the 6xy, I'm going to subtract it to the other side. My goal is to isolate the dy dx, but I see that there are 2 of them on that left-hand side. Since there are 2 of them, there in each term, I know I can factor that dy dx out of both of those. So in this first term, that's going to leave me with a 3x squared, and in the second term, that will leave me with 1. Remember, a good way to check that is if you distribute the dy dx back in, you'll get what you started with. So make sure you have that 1 as a placeholder in that spot. Okay, the goal is to isolate dy dx, so the last step then is to divide both sides by 3x squared plus 1, so we end up with this, negative 6xy over 3x squared plus 1. And we just found dy dx. We found if we had a point on the curve, we could find the slope at that point, but that's not what it asked. So we're just going to stop. Okay, now this will be the last one. I want you to find dy dt for this function. Actually, I'm going to make it more interesting. Not this one. I want to use this one instead. Let's go back to our circle. This time we're going to look at how are these values changing as time goes by. So imagine if, like an ant, we're crawling around the edge of a circle, And as time goes by, how is the rate of change of that ant? What does that look like as time goes by? So let's take a look. I'm going to differentiate this now with respect to time. So this is why I was doing everything I have been doing up till now, is for this situation here where we've got a completely different variable. So this was with respect to time, this is with respect to time. All right, let's find the derivative of x squared. We've got the outer function, which is the 2, the squared, I mean, so I'm going to bring the 2 out in front, and that's x to the first, times the derivative of the inner, so that's dx dt. How is x changing as time is changing? We don't know. Okay, now we'll find the derivative of y squared, outer function, bring the 2 out in front, multiply by the inner function, derivative of the inner function, which is dy dt. And with respect to anything, since 5 is a constant, its slope or its derivative will be 0. Now remember, the question asked you to find dy dt. In other words, let's isolate that variable. So I'm going to subtract this entire thing over to the other side because we want to try to get everything away from the dy dt. So we have 2y dy dt equals negative 2x dx dt. We're trying to isolate the dy, so I'm going to divide both sides by 2y. I won't skip any steps on this one. Negative 2x dx dt divided by 2y. Now what I can see is that both of these 2, since everything is multiplication, those can reduce. So our final answer then is dy dt equals negative dx dt over y. Now, why are we doing this? Good question. We're going to use this in an application here in the next unit. I just wanted you to practice, that's a horrible highlight color, sorry. I just wanted you to practice this right now before we actually put this to some form of application. So getting down the differentials, the derivatives, is the important part right now.